Hey guys, it's Mr. Post, and on today's video we'll be discussing removing an electron from the electron cloud. That means removing the outer valence shell electrons from the electron cloud. We're specifically talking about the valence shell electrons, and also learning a new trend on our periodic table, and this time it is for ionization energy. In the previous video we watched the trends for atomic size. The second trend we're discussing is going to be ionization energy. So in a big picture setting, what I want you to look at is being able to, at the end of this video, try to look at the periodic table and say where on the periodic table is it going to be easiest to remove an electron from an electron cloud, where it's going to be hardest, and also to be familiar with this new term ionization energy. And once again, to be able to locate and distinguish the trends in the periodic table for my groups and my periods. My first question that I'm throwing out at you here is to examine these pictures. Alright, let's examine these pictures. We have two atoms here. One is lithium and one is sodium. Lithium has two energy levels, and it has now its valence electron right here on the outside of the second energy level. Sodium is actually directly below lithium on the periodic table, and I have 1, 2, 3 energy levels, and this valence shell is located on the outer energy level. So my outer energy level in this case is a 2s1, and my outer energy level here is a 3s1 for the third energy level, s orbital, 1 electron. And the question I'm asking you, which nucleus has a stronger grip on the outer electron, the larger atom or the smaller atom, and why? Please press pause, consider this question, and make an answer. A good idea would be to have a copy of my notes along with you, and do these on the piece of note paper as well. You can download the notes from my website too. Alright, so take a second to answer this question. Which one is a stronger grip on its outer electron? The answer is going to be lithium right here. Lithium has a stronger grip on its outer electron, mainly due to distance. Okay? There is a smaller distance here, and if my nucleus has a positive charge and my electrons have a negative charge, there is this attraction going on between the two, and the closer they are together, the stronger they are attracted. Over here, let's check this out. 1. There is more shielding by my inner or core electrons. My inner or core electrons provide shielding, which reduces the attraction to the outer energy level. I also have this issue of a farther distance. The farther distance from the nucleus means my outer shell electrons not being held on as tightly either. So simply, in plain English, it's going to take more energy to remove an electron from a smaller atom. It is simply due to a stronger grip. Alright? The smaller atom has a stronger grip on an electron, therefore it's going to take more energy to remove it. With that knowledge, I want you now to imagine this slide as a periodic table. Okay, so imagine this yellow box down here as a periodic table. Where on this yellow box would you consider to be the hardest place to remove an outer shell electron? And where on this periodic table would you say is the easiest place? And I'm giving you 4 corners to choose. Each one has a question mark in there. One of the corners will be the most difficult place in the periodic table to remove an electron. One is going to be the easiest. And here's a little hint, guys. It actually has to do with the size of the atom. We learned the periodic trends for the atom in the previous video. So take 2 seconds, take a guess. Okay, well, in the previous video we learned that the atoms get bigger going this way. That the atoms grow in atomic size from the right to the left. And over here on the right, I had some small atoms. I had a cluster of small atoms. Alright, a cluster of small atoms. Over here, we had some bigger atoms. And finally, down here, we had the larger atoms. And that's the case, okay? So I did have some big atoms down here. So atomic size increased over to the left, and atomic size also increased going down the periodic table. And atomic size is increasing going down the periodic table. So where is it hardest to remove an electron from an atom on the periodic table? Over here. And the previous slide, we just saw that it takes more energy to remove electrons from small atoms. And that's the case. The small atoms are located over in this corner here. This is where the small atoms are. It's very difficult to remove electrons from these guys because they're small. Okay, this picture represents a very large atom. And the atom is getting bigger going down the periodic table, bigger going to the left. Where is it easiest to remove an electron? Down here. It is easiest to remove an electron from this corner of the periodic table. So it's easier to remove an electron going to the left as the atom gets larger, and also easier to remove an electron as I go down the periodic table. There is a term for this, and the term is ionization energy. It is simply going to be the amount of energy needed to remove the outermost electron. So what I'm saying, where in the periodic table is it easiest to remove an electron? I'm saying, where in the periodic table is an atom going to require the least amount of energy in order to pluck away its outermost valence electron. Now, there's more than one electron in your electron cloud, and the first ionization energy refers to the energy needed to remove the very first, or the outermost valence electron. And there's going to be a little sequence here. In order to remove the next valence electron, because you have more than one valence electron sometimes, that's called second ionization energy. And it goes on for third ionization energy as well, and it also goes on for fourth ionization energy too. But once again, it is the amount of energy needed to remove the outermost electron. So if I go back to this slide again, lithium has a higher ionization energy because it takes more energy to remove electrons from smaller atoms. So I would say this has a very, not a very high, but a higher ionization energy needed to remove the outermost electron, and this has a lower ionization energy. Once again, what is that based on? It's strictly based on atomic size. Whoa, sorry about that, guys. Did not expect that line to appear there. The periodic trend, the very last objective of the lesson, the periodic trend simply says, in my groups, what is the trend for ionization energy? And the arrows here show my ionization energy is going to increase as I go up a group, because as I go up a group, the atoms get smaller. So every single group on the periodic table, the trend is going to be to increase your ionization energy upwards. From large atoms to small atoms, meaning it is going to take more energy to remove an electron from boron than it is from thallium. It's going to be easier. Alright, that's the period trend. The group trend is simple. That is the period trend, rather. I call that the group trend. That is the period. Excuse me, that is the group trend. Alright, groups are vertical columns. The period trend, going left to right on the periodic table, is going to be my ionization energy is going to increase over this way where the atoms get smaller, right over to iota. Now I chose iota as a character to put on fluorine because fluorine represents a small atom. And iota is a small character who's kind of really tough, and I really like Star Wars a lot, so I'm kind of fond of it. Now, if iota is a small atom that represents something that's very, very strong, I chose the opposite here. I chose Big Bird. Okay, now I watch a lot of Sesame Street because I have a lot of little kids, and I get a little tired of Big Bird sometimes. So Big Bird to me represents an atom that is very, very big, but also very, very weak. Alright, so Big Bird is a large atom. Alright, very easy to steal an electron from a large atom. Why? Because you're weak. So I chose Big Bird to represent something that's big but weak. And Yoda, my man over here, the Jedi Knight, You're not going to mess with him. You're not going to pull an electron away from his electron cloud. He's something that's small but strong. So the group trend is going to be to increase in ionization energy from the bottom of the periodic table to the top, and the period trend is going to be to increase from left to right. And this is opposite of atomic size. All right, guys, there you got it. That's going to be ionization energy, periodic trend, and also learning how to remove an electron from an outer shell. Last thing we need to cover now is just a simple assessment question. Okay? Which of the following elements would it take the most amount of energy to remove an electron? Or which element has the highest ionization energy? Higher ionization energies come from small atoms. The smallest atom in this group is going to be neon. It is the farthest to the right. It has the highest ionization energy. Okay, in this group, guys, this is one of our groups. It's group 3, or also known as 13. Which atom has the highest ionization energy, or which requires the most energy to remove an electron? Take 2 seconds, give it a shot, and press pause. Alright, dudes, the smallest atom in this group is going to be boron. Boron, therefore, also has the highest ionization energy. It takes the most energy to remove an electron from that outer shell. Okay, guys, that's ionization energy. Those are the periodic trends. That's how we remove electrons from our outer shells, and which atoms require the most amount of energy in order to remove an outer shell electron. Alright, guys, thanks for tuning in. Best wishes. I'll catch you later.